In addition to resistive sensing, capacitive sensing is another very common transduction method for sensors. And the simplest way to think about a capacitive sensor, in the same kind of idea that we thought of a resistive sensor as a block of some material that we were then deforming, the simplest way to think of a capacitive sensor is as two parallel plates. Those capacitive plates are going to have some area A, that's the overlap area of the plates. They'll have a separation distance between them of, let's call it G0, so that's the initial gap. And then they have some dielectric, and we're going to denote that by epsilon r. So epsilon r is a relative dielectric constant in comparison to the dielectric of air or vacuum, which is written as epsilon naught. And this is a pretty valid model as long as, just thinking about this parallel plate model, it's a pretty valid model as long as this gap between the plates is a lot smaller than any of the length and width dimensions of the plates themselves, for example. And given that, we can calculate a capacitance of these parallel plates. Our capacitance is going to be based on those dielectric constants, epsilon naught and epsilon r. It'll also be proportional to the overlap area of the plates and will be inversely proportional to the gap between the plates. So epsilon naught in this case is given as 8.85 times 10 to the minus 12 farads per meter. So let's get an idea of what kind of capacitances we might be seeing with this basic setup. If I give myself an area of, let's start with something like a millimeter squared, so 1 millimeter on each side, I'm going to give myself an initial gap of 1 micron. And this is something where microelectromechanical systems comes into play because I can make very small gaps, and capacitive sensors are prolific. They're common, very common there. And then I'm going to say I have air between my conductive plates here, so my epsilon r is 1 for air. And with this I can calculate my capacitance. And here I'm going to get these two 10 to the minus 6's are going to cancel, and I'll just get 8.85 times 10 to the minus 12 farads, or 8.85 picofarads, which seems pretty small, but is a pretty typical capacitance at these kind of scales. Right, but despite the ubiquity that you find these kind of parallel plate sensors, these are what go into a lot of the inertial sensors that we've talked about, a number of other humidity-based sensors, soil moisture sensors. There's a lot of sensors that are based on these kind of parallel plate model. But what you probably interact most commonly with that's a capacitive sensor is a touchscreen right here. And this is a slightly different setup than a parallel plate, and unfortunately it's really challenging to model, so we're just going to talk about this qualitatively. So the basic idea comes from the fact that if I have two parallel plates, and now I'm just going to look at them end on, so I can see my gap very clearly and anything alongside that. And so let's say I've applied kind of a plus, my plus charge is on this plate, and my negative charge is on the bottom plate here. So I'm going to get electric field lines between these two plates like this. And if I have the case where that gap is very small in comparison to the other dimensions of my sensor, then most of the capacitance, most of the electric field that is stored in this capacitor is going to be in this lines that I've drawn right here. But you also have what we call fringing fields. So I also have field lines that are going like this around this sensor here. So pretty much all the stuff out here, outside of my plates, I think of as these fringing effects. And like I said, unlike the kind of parallel plate bit, these fringing effects are really difficult to model appropriately. But I can think about how I would design sensors to take advantage of these changing. So the first picture of this, I'm going to have kind of a sensor electrode that's kind of flat on a surface, and this is something that I could design into something like a printed circuit board, or I could print on a screen and do that with some kind of transparent conductor. And next to that, I have a grounded electrode. So here's my sensor, and I have my grounded electrode here. So in this case, this gap between these plates right here is large in comparison to this dimension, so these fringing fields are going to be pretty dominant, and I cannot model this based on a simple parallel plate capacitor. So I'm going to have all these fringing fields right here, and I'll have them on the other side of this as well, but very commonly what you'll see is somebody puts a shielding layer on the back of this right here, so that all of those field lines are kind of directed towards the surface that you're trying to measure something on. And it's, once again, very difficult to model analytically, but I have a basic model that says as the sensor area increases, my sensor sensitivity is also going to increase. It's not necessarily in a linear fashion, but bigger sensor area, more sensitive sensor. Right, and this is really working by, as I'm moving my hand or some other substance, maybe it's a fluid or something, over this, as either that dielectric constant around these two electrodes is changing, or as I'm providing another ground path, say my finger over this, I'm actually measuring then a change of capacitance at that sensor. Right, I'm changing the overall capacitance of this system. Another way to do this is just with a single electrode, and especially if I'm trying to do some kind of gesture recognition with a person, or somebody's going to be coming near this. So this is my sensor electrode here, and I have my hand up here, and that hand is effectively acting as a ground because I end up being grounded. And so I'm creating a capacitance like this, and as I move my hand closer, I'm effectively moving my electrode closer, and I'm going to get an increase in capacitance. So as this distance effectively decreases, then my capacitance is going to increase. So these are just a couple qualitative ways of how we might use fringing fields as our sensors as well, instead of just a parallel plate model. Alright, but going back to that parallel plate model, and I'll redraw my plates here, I have a number of different parameters that I can possibly change that will ultimately give me some change in capacitance from my nominal position. So a fairly obvious one looking at this equation is changing that dielectric constant. So if I change epsilon r, and this is something that could happen for both the fringing field effect and this parallel plate effect, if I change that epsilon r, I'm going to be changing my capacitance. And this is used in a lot of fluid level sensors, in a lot of soil moisture sensors, a lot of other kind of material testing, a lot of applications like that. Another fairly popular configuration would be to actually have this top plate suspended in some kind of mass spring damper system. And this is very common in the inertial sensors that you also have on things like your phone or a quadrotor, for example. And in this case, as I am accelerating, for example, maybe this is a larger mass, the position of this plate is going to change relative to this plate. So if I define the position of this top plate as x, then I'm changing my gap. And my new capacitance is going to be epsilon naught, epsilon r, a over that nominal gap plus whatever displacement this top plate has undergone. And a final way to think about things that I can change, I can do that same thing from the side, and I can change the overlap area. So my gap would remain constant, but in this case I'm changing the area that these plates overlap. So things would move basically like this relative to each other. And so if I call this dimension, let's say L right here, I'm going to be changing L and say this is my width, that will stay the same. So if I define this position right here as Y, right, so the more I move, the less overlap area I have. My capacitance in this case is going to be those dielectric constants my width, that's staying the same, times L minus that displacement. So I've lost that overlap area over my gap. Let's do a quick example using one of these to get some idea of what kind of change in capacitance I might be seeing. And let's pick the change in gap. So this plate can be moving back and forth vertically here. My delta C is of course going to be my new capacitance after I've displaced everything minus my nominal capacitance. Whereas in this case that's going to be epsilon naught epsilon r times A 1 over my new gap minus 1 over the original gap. Let's say this is happening in air. I have an A of 1 millimeter squared, or 10 to the minus 6 meters squared, and I have an initial gap of, let's give myself 2 microns, that's something that we can do in our clean room, and a displacement of, let's say, only 100 nanometers, or 0.1 microns. So it's a pretty small displacement. Let's see what kind of capacitance change we would have to be able to detect in order to pick that up. This will give me a delta C of -2, approximately -2 times 10 to the minus 13 farads, or approximately -200 femtofarads. Or I could think of that as 0.2 picofarads. So that sounds pretty small, but there's a lot of capacitive electronics out there and interface circuits that we'll talk about that can pick up sub-femtofarad changes of capacitance. So you can do some really nice displacement sensors, for example, and ultimately inertial sensors with capacitance.